Good morning, everybody. Welcome to the Friday seminar for this week. My name is Nathan Fox from the Bryan Research Centre. Well, thanks everyone for joining us today here in the room and also online. Before we begin, on behalf of the SMI and the University of Queensland, who are based here in Brisbane, we first like to acknowledge the traditional owners of the land on which we meet today, and we pay our respects to their ancestors and to their descendants. Today, it's a pleasure to introduce our speaker, Sebastian Hoerning, from the University of Queensland Centre for Natural Gas. By way of introduction, Sebastian holds a BSc, an MSc and a PhD in environmental engineering from the University of Stuttgart in Germany. After finishing his PhD on process-oriented modelling of spatial random field using copulas in 2016, Sebastian joined the Centre for Natural Gas here at the University of Queensland as a research fellow. Sebastian's research focuses on developing geostatistical techniques and inversion approaches which allow more realistic representations of environmental systems and their dependent variables. The title of today's talk is Copula Geostatistics, because normal isn't always the best choice. And Sebastian has let me know that this is going to be quite a high level, but certainly opportunity for some participation from the audience as well. So we're looking forward to that. So without further ado, I'll hand over to you, Sebastian. Thank you.
Thanks, Nathan. Good morning, everyone. And so what am I going to try to tell you today? I will try to tell you that the world is not normal. And given the current circumstances, I think we can all agree. But this is more about the very specific part of normality. It's that I want to show you that most spatially distributed variables do not follow multivariate normal distributions. And I hope that by the end of the talk, you will understand what that actually means, why it can be a problem, and how copulas can help you to spot those issues and also help you to solve some of those issues. All right, so therefore, I will first start with a quick refresher on geostatistics. So what is a geostatistical problem? And then we move on to what is normal in geostatistics. And then I will show you with a lot of examples why normality can be a big problem when we talk about geostatistical data. Then I will move on to copulas, and I will give you very high-level information on copulas. So we don't go into many equations. There are, I think, only 4, and you can ignore them. I'll tell you a bit about copulas in general. Then we move on to spatial copulas and copula-based functions of dependence, like the spatial asymmetry function. And then how can we use copulas to model? All right, so geostatistics. What is a geostatistical problem? A geostatistical problem always arises when we have spatially distributed data, which we only sample at a certain number of locations. So here we have a map of the German state of Baden-Württemberg. It's in the southwest of Germany. It borders France to the west and Switzerland to the south. And the federal government has an environmental department which has roughly 2,000 groundwater measuring points. So it's like groundwater bores where they take groundwater samples to measure groundwater quality parameters like chloride, nitrate, pH value, and so on. So we have this sort of data set, and now the question that arises is, what is going on in between those measured points, right? So we want to be able to make an estimate of what is going on in between. Ideally, we also want to know how good that measure, like that estimate is, like how much can we trust our estimate. For certain tasks, we want to be able to get more than just one estimate. So we want to be able to simulate possible realizations of the parameter of interest. And how can we do this? Well, we can do this using geostatistics. So using geostatistics in general, we can get an estimate of a value at each unobserved location. And geostatistics originally comes from the mining industry, from South Africa, actually. A guy called Kriging, he used to work for, I think, a gold mine in South Africa. And he initially came up with the idea of Kriging, so it's called after him. And this idea was later on put into some nice equations by the French mathematician Matterhorn. And basically all geostatistical techniques follow the main idea of Waldo Tobler's first law of geography, that everything is related to everything else, but things that are like near things are more related than distant things, which naturally makes sense. Okay, so when I say geostatistical techniques, and I say traditional geostatistical techniques, then I mean Kriging, all the different types of Kriging, sequential Gaussian simulation, which would be one of those where we can simulate realizations of the parameter of interest, or turning band simulation. So what is the problem with those, or what is the normal part of those techniques? The normal part is that all those techniques assume multivariate normal distributions, or Gaussian distributions, or whatever you want to call them. I just say normal for the rest of the talk. So what does that mean when I say they assume multivariate normal distributions? That means that we can define this distribution using the first two statistical moments. That means the first moment is the mean, and the second moment is the variance. And for geostatistics, that would be the variogram, which is basically a function of distance. So here we have a typical variogram. On the x-axis, you have the distance. So it's a separation distance between pairs of points. And on the y-axis, you have the variogram value, which is pretty much a measure of variance as a function of distance. So it tells you when you are very close, you have a low variance on average in your data. And the further you get away, so like the bigger the spread is distance-wise between your data points, the higher the variance. Okay, so close things are more related than distant things. So that's all you need to specify a multivariate normal distribution. So now I say, well, what about the third statistical moment? And what would the third moment be in geostatistics? Or what is the third moment in general? That's what I expected. So let's do a quick excursion back to our statistics lectures at uni. So here we have three data sets, A, B, C, and D. A, B, and C. And you can see that they are obviously different. So it's just histograms. So on the x-axis, we have the values. On the y-axis, we have the frequencies. Now let's analyze those three data sets using the first two statistical moments. First moment is the mean. Second moment, standard deviation in this case, which is just the square root of the variance. Right. So according to those measures, those data sets are identical. Right? They are the same. So what's the problem? So obviously, the first two moments are not enough to distinguish between those different data sets. So what can we do? We can have a look at the third moment, which in univariate statistics is the skewness, right? So the skewness tells us that for dataset C, we have pretty much zero skewness. That is because it's symmetric. So that is based on a normal distribution. So no skewness. Dataset B has a negative skewness, so it's skewed to the left, and dataset A has a positive skewness, so it's skewed to the right. Okay, so the skewness is a measure of asymmetry in univariate statistics. And here we have the equation. It's one of the four equations that I will show you today. It's a very simple one. I just showed it because it will come up again when we talk about spatial asymmetry. All right, so point here is the first two moments are not enough to distinguish those data sets. We need the third one, which is a measure of asymmetry. So coming back to spatial problems, what is asymmetry in a spatial sense? Okay, and because it's very difficult to do this with subsurface data because we only have points, I always use surface equivalence because we have a full picture and it's much easier to see things on a picture than on points. So what we have here is two digital elevation models somewhere in the Ukraine. Okay, what I did to those pictures is I removed the actual values. So I normalized them to be between 0 and 1. So I took the ranks of the actual elevation. A 0 means the lowest elevation, and 1 means, where's my mouse? Here we go. 1 means, you can't see my mouse, right? No. Anyway, a 1 means highest elevation. So blue is low, red is high. And then I have two versions because in one of those pictures, I inverted the color bar. Here we go, right. And now the question is, you look at those pictures, and can you tell me which one is the right one? So which one is not the one that I have inverted the color bar?
Yeah, right. Oh, sorry.
Left?
Yeah.
So left is the right one? So it's the correct one? Yeah. Yeah. Why?
Because you can see it's a drainage network.
Exactly. So you just know that this is how it has to look like, right?
Yeah.
Yeah. So yeah, this one would be, it wouldn't make sense. Like they would all be small lakes, and as soon as it rains, they would fill up, right? So you can see the drainage network. Good point. Yes. So we can see that. And why can we see that? We can see it because we naturally know it, and also because lakes, valleys and mountains are different structurally. From a structural point of view, they are very different. They come from different processes, right? So different processes act when mountains and valleys are created, and we can see that. So the left one is the correct one. The next example, a little bit further away than the Ukraine, it's on Mars. Again, it's just a digital elevation model, and same question. I did the same thing. I removed all the actual values, it's normalized, and one is inverted. Which one? Left one again, because we have those deep craters, right? On the other hand, we would have very strange mountains, which, yeah, it's not a thing. So we know this one is the correct one. So what are our findings so far? So we know that the first and the second statistical moment are often not enough to really distinguish between different data sets. From those pictures that I just showed you, we know that upside down can very often be recognized. And if we cannot recognize it, we at least can see that there are structural differences between high values and low values. And that is because these structures are not symmetrical in a spatial sense, right? So we have asymmetry in the structures between the high values and the low values. And that is because those structures are all not normal or non-Gaussian. Right, so the question now is, how can we spot such non-normalities or asymmetries if we have point data, if we don't have a full picture? And how can we quantify this? And then subsequently, how can we use those information to model? And therefore, we can use copulas. So here we just have a bit of a history on copulas. So the first time that copulas appeared in the literature was in 1959 by a French mathematician called Sklar. He was investigating the just multivariate distribution functions in general. In 1999, they were introduced into financial applications. And in 2006, someone did an overview statistics on copulas. And they said they are more or less widely used in statistics, finance, and mathematics. And only a very small part is in engineering and economics and all that stuff. And a fun fact, could be good trivia question knowledge. The Gaussian copula, which is just one of the many copulas that are out there, was initially blamed for the 2007 and 2008 financial crisis. So this bloke here, Lee, he came up with the idea of using copulas for financial applications for the stock market. And it worked really well, actually too well. And then people got really greedy and they abused it or misused it, and at some point it just went horribly wrong. Later on, it's been proven that it's not the fault of the copula, it was just that people just used it incorrectly and everything went to shit. But yeah. Okay, so what are copulas? Copulas are multivariate distribution functions defined on an n-dimensional unit hypercube with its univariate marginal distributions being uniformly distributed between 0 and 1. Whatever that means, right? A copula contains all the essential information about the dependence between random variables. And I will show you in a minute what that means. And because of the point 1, that we have all univariate marginals being uniformly distributed, copulas have a greater modeling flexibility, because once we have a copula which describes the pure dependence of the random variables, we can then just choose whatever marginal distribution we want, because we can easily transform a uniform marginal to any marginal that we need. What does that mean? Right, 3 data sets again, this time bivariate data sets. Could be stock prices, could be whatever. I just made it up, completely made up. Variable X, variable Y, and the corresponding univariate marginal distribution on the sides on the histograms, okay? So when you look at those and I ask you, which of these data sets has the strongest correlation? What would you think? This one is the strongest? Okay. Then I ask you, which one has the strongest correlation for high values? This one? Okay. Actually, they all have exactly the same correlation. So when we calculate the copula of those data sets, that means I remove the marginal distribution. So I rank each variable between 0 and 1, and I put that into a scatter plot. Then all 3 result in exactly the same copula. And we can see that the marginals, the univariate marginals of the copula, are uniformly distributed. Okay. And what is also interesting is that even though it doesn't look like it in this case, the high values have actually a stronger dependence than the low values. Okay, so that's a copula. The copula tells us the pure dependence, the actual underlying correlation, independently of the marginal distribution. Because the problem is that in this case, the univariate marginal distributions are very skewed. And those skewed distributions make it very hard to actually see the true correlation between variables. So when we remove that skewness from the distribution and we go to uniform distributions, we can see, oh, right, actually, the high values have the strongest dependence in those data sets. So that's what copulas can do. When we go to spatial copulas, in 2006, my former boss in Stuttgart, Andras Spardoshi, he came up with the first actual spatial copula. And he said that, oh, I was actually lying, I have 5 equations, I'm sorry. He said, so he came up with the definition of a spatial copula, and he said that it has to have the same properties as every geostatistical technique, so we have to have translation invariance. That means a spatial copula is actually not dependent on the actual location, but on the separation. So it's a function of distance, just like every other geostatistical technique. The actual location itself is not important, it's always just the separation distance. The simplest version of a spatial copula is called an empirical spatial copula. And so it's a visible version of a copula, because copulas are very high dimensional. but as soon as you go beyond 3, you can't really visualize it anymore. And even 3-dimensional is hard to visualize. So we always stick to 2-dimensional if we want to visualize things. And this is a bivariate empirical spatial copula. It's a generalization of a variogram, and we use kernel smoothing to get the actual density. Let me show you how we can create such a copula based on spatially distributed data. So if we have a data set like this, so we have observations at those locations here, then we have to first, the same with variograms, right? So you have a point, you have a point data set, you need to define a separation distance first. So we say for a certain distance h, which is like an approximate distance, you can never go for an exact distance because you never really have exact distances, only for one pair, but then you only have one pair in a distance class. So you want the distance to be between, let's say, 100 meters and 150 meters. And you select all the pairs that are separated by that distance. So when we do that here, we have all those pairs. And there might be more, but I was like too lazy to get all the arrows in there. Okay, so we select those pairs. Then we define a regular grid on the unit square. So as I said before, a copula is defined on an n-dimensional unit hypercube. So the 2-dimensional version is a unit square. So we define our grid on a unit square. And then every pair corresponding to every pair of points in our data set then corresponds to 2 points in the copula. So let's look at those 2 points here separated by h. So it gets 1 point here and 1 point here because it goes both ways, right? So this point is separated by h from this point, and this point is separated by h from this point. So we get 2 points into our copula. And then we do this for all the points that we've got. And then we get such a scatter plot again, which I showed you before. But then sometimes we have so much data that we have a lot of dots on top of each other, and it's very hard to see what's going on. So what we do then is we, first of all, we count the pairs in the corresponding section of the grid, and we divide it by the overall number of points. So we get the bivariate frequency. So that means we basically create a 2-dimensional histogram, a normalized 2-dimensional histogram. And then for better representation, we use kernel smoothing. So we basically color the thing up, okay? Because as I said before, when we have too many points, you can't really see how dense the points are in one of those grid blocks. So then we use kernel smoothing for better visibility of the actual density. And you can already see, well, that thing is asymmetric with respect to the secondary diagonal, okay? So let's have a look at an actual example. So when we go back to the digital elevation model in the Ukraine. So here we have the variogram of that elevation model. Sorry, this is in pixels. One pixel is 50 meters. And here we have also the covariogram and the rank correlation function, which is basically the copula equivalent of a variogram, where you, once you remove the actual values, you get the actual rank correlation function. And then we have the empirical spatial copulas for that data set. And you can already see that they are asymmetric. It's a bit hard to spot, but when we zoom in, we can see that we have a higher density, so we have more red and orange in the lower left corner than we have in the upper right corner. So that means we have a stronger dependence for low values for small separation distances. And then it actually changes. So at this point, we can say, well, for that separation distance, it's pretty much symmetric. But then it swaps around. So in this case here, we have a higher density in the upper right than we have in the lower left. So that means for larger separation distances, the high values have a stronger dependence. If we look into another example, that is an outcrop of the Borden aquifer in Canada. So it's an aquifer that has been really almost abused by researchers to get really, really good data from an aquifer. And what they did is, first of all, they have this outcrop. They did a lot of experiments, but they also have two cross sections where they drilled very closely spaced wells. They chopped the cores up into 5 centimeter sections, and they measured the hydraulic conductivity of the material. So when we analyze those hydraulic conductivities using copulas, we end up with those copulas. And we can see that they are extremely asymmetric. So that means that the high conductivities, pretty much for all separation distances, have a very strong dependence, while the low conductivities only have a strong dependence for small distances, and then it's pretty much all over the place. So we can't really say much about the small conductivities, while we can say that the high ones are strongly correlated. Another example goes back to the first one that I showed you with the groundwater quality parameters. So, as I said, they measured pH, sulfate, nitrate, and chloride. And we investigated all of them, but chloride is a very good example. So here we have two empirical spatial copulas for chloride, one for a separation distance of 5 kilometers and one for 30 kilometers. So what can we see here? We can see that for 5 kilometers, we actually have, I'm sorry for the color bar is horrible. Like, I don't know why it goes up to 15. But we can see that we have higher density for the very, very high values up here. And it's because for small separation distances, it's actually anthropogenic chloride. So farmers use fertilizers on their fields on a small scale. So for the small scale dependence, those very high values, they cluster. So we have a strong dependence for high values on a small separation distances. While when we go to larger separation distances of 30 kilometers, that dependence is gone. So now we have a strong dependence for the very low values, right? And those low values are the natural chloride that we have naturally in the system. So because it's kind of like the background concentration, and that clusters or like has a dependence for larger separation distances. So those things, it actually makes sense, and it's explainable, right? Okay, so what have we seen so far? We have seen that empirical spatial copulas are an empirical tool which can help us to identify spatial asymmetry from point data. That we can use kernel smoothing to get a nice colorful picture, which is better than just a scatter plot. We saw that those copulas are symmetric with respect to the primary diagonal, but they are asymmetric with respect to the secondary diagonal. So now we can detect it, but we still can't quantify it. So how can we quantify this asymmetry? And therefore, we come back to another equation. So this one, which is the spatial asymmetry function. And if you remember what the equation for the skewness looked like, it was very similar. So we have we had the value minus the mean to the power of 3. So we have the power of 3 in here. So it's a very similar equation, but it's an extension to the skewness. So now we have a spatial asymmetry function, which is a function again of distance. So you can imagine it as taking those copulas that we create for different separation distances, and you overlay it onto this unit square. And this unit square tells you the contribution of each point in the copula to the asymmetry function. So if we have strong dependence for high values, we get a lot of positive contribution. If we have strong dependence for low values, we get a lot of negative contribution. Okay, so what does that mean for our example? Let's go back to the Ukraine. So again, we have the variogram, the copulas, and now we have the spatial asymmetry function. We have two functions, they have different definitions. The blue one is the important one. That's the one that I just showed you. So we can see for small separation distances, we have a negative asymmetry because we have more density in the lower left of the copula. So stronger dependence for low values. Then after 3, this one here is symmetric. It has 0 asymmetry. And then we move on to a positive asymmetry for larger separation distances. Okay, so we can now quantify that. Right. So another example to show why this is a problem when we have the assumption of multivariate normal distributions. So here I simulated 2 random fields. They are somehow similar, but also different. What is identical is their values. So if you would take all the values from each field and put it into a histogram, they would be exactly identical, a uniform distribution. So all uniform, that means they have the same mean. When we look at the variogram, they are almost identical, not quite, but almost identical. So again, the first and second moment are not enough to distinguish between those 2 fields, even though we can see that structurally they are very different. And it becomes even more obvious when we divide the fields up into their 35% lowest values, always in blue, and the 35% highest value in red. So we can see in that case, which is a Gaussian field or like a multivariate normal field, the blues and the reds form very similar structures because the field is symmetric. In this case, the blues and the reds form very different structures. So we have a connected network of those blues while we have those big blobs of high values. And now we have the spatial asymmetry function, which we can use to actually quantify this asymmetry. So that field has pretty much 0 asymmetry. There's always a small chance of like getting a little bit of asymmetry just because it's a stochastic process, so you never get exactly 0. But in this case, we have a very strong positive asymmetry because we have those big clusters of high values. Okay, so we can detect those things now that we have a 3rd order spatial moment. Oh, sorry. There you go. All right. So what did we learn so far? Well, we saw that the spatial asymmetry function helps us to describe the difference in dependence for different quantiles. So we can now distinguish between strong correlations for high values or low values rather than just an average description of dependence. It's a 3rd order spatial moment, just an extension to the skewness in univariate statistics. And it's a very useful extension to a variogram because it just gives you more insight into your data. And the last example showed that multivariate normal fields have no spatial asymmetry. So when we use any approach based on Gaussian distributions, we cannot model this. But now the question is, how can we model it, right? So far we have analyzed it and we have quantified it. But now we want to be able to use those information in any subsequent modeling task, right? Therefore, we can use copulas again. But we need theoretical copula. So we need a copula model. And that's where we have a bit of a problem because in terms of spatial copulas, there's not that much out there. There's the Gaussian copula, which we can see here. So that's the equation for the Gaussian copula. And you can see it looks very much like a multivariate normal distribution. That's the covariance matrix. Sorry? Oh, sorry. Yes. So that row is part of the covariance matrix. So depending on how strong the correlation is, that is basically the correlation coefficient.
So that's a whole other equation.
Oh yeah. Oh yeah. This is, like as I said, like I'm not going into details. Like we can fill pages with equations there, and yeah. So that's a matrix. Yeah. And that matrix depends on the variogram. So the variogram itself has parameters, right? So it has a sill, a nugget, and a range, and the actual type of variogram. That all goes into the covariance matrix, and from that you get the correlation for those. Yes, yes. So it's just two bivariate Gaussian copular densities, just for different parameters to show what we can get from that. But you can see they are symmetric, so not very useful. Luckily, we have one copula, which is called the V-transformed copula, and that V-transformed copula is also based on the Gaussian. So you can see some similarities in there, but there's a transformation which looks like a V in a high dimensional space, and that transformation makes the copula asymmetric. Okay, so again, we have different rows and different other parameters, and again, we have a variogram in there. So it's a lot of parameters, very high dimensional, but we can get asymmetry. So what does that mean if we actually want to use them for modeling? Let's go back to Canada. So we have our data set, and we want to be able to represent the asymmetry in this data set with theoretical copulas such that we can use them for modeling. That means we have to fit the parameters of that copula to this data set. So here we have the empirical copulas again, the ones I showed you before, just a few less because I didn't want to overload the picture. And now the task was to find the parameters of the V copula such that the theoretical copula matches the observed copulas, right? And you can use different fitting algorithms for that. You can use maximum likelihood methods or least squared fittings or whatever. But you can see, well, it's actually, they resemble the actual observations quite well. And here we have the observed rank correlation in green, and the blue one is the one that we get from the theoretical copula that we fitted to the data. So and the asymmetry function. And you can see it's quite a good fit. So now we could use those copulas for simulation purposes or interpolation purposes. So how would we do that? Let me quickly walk you through the steps for sequential simulation using copulas. It's pretty much like sequential Gaussian simulation, just that we replace the multivariate distribution with the copula. Okay, so what does that mean? Copulas work in rank space, so we first have to transform all the observations into the CDF space or like rank space. So we remove the actual values. We always work in the space between 0 and 1, and that gives us the freedom to use any sort of marginal distribution that we want for the modeling. We define a random path through all the unsampled points. So here we have, let's say this is our simulation domain, and the green dots represent our observations. The violet dots represent unsampled locations where we want to simulate a value. So we define a random path, which goes randomly from one unsampled location to the next unsampled location. And at the first point, so we start here randomly, we have to calculate the cumulative conditional distribution at that point, conditioned on the observations. On M original observations, and that M again can be defined as you wish. So usually we go for the nearest 10 neighbors or something like this. So, and then we calculate the conditional distribution and at this location here, and the conditional distribution is a conditional copula rather than a conditional Gaussian. That's what you would do for sequential Gaussian simulation. So when we do that, we calculate this distribution, and then let's say this is our conditional distribution at that location. Then we use Monte Carlo simulation to draw a random number. We use that random number, go into the conditional distribution, get the corresponding value, and we assign that value to that location, and now it becomes green. So that is that we add that value to the set of conditioning points, and we go through all the other points until all of them have a simulated value. Okay, so as I said, just like sequential Gaussian simulation, just that we replace the Gaussian part with the copula. And if we want a second realization, because we are interested in possible realizations, we would just start with a different random path. Okay? So what can we get? We can get conditional spatial random fields with structures like that. So highly asymmetric spatial structures. In this case, we have those strongly connected paths of very high values. This is the one that I showed you before with like the big blobs of high values, and another example. So those fields, they can be conditioned on your observations. So they are unbiased in terms of conditioning, and you can represent any sort of asymmetry you want. Okay, so what did we learn so far? We learned that we can use theoretical spatial copulas, which we can fit to our observations, and we can use them for conditional simulation. For example, using sequential simulation. There are different ways to do that, but sequential simulation is probably the most straightforward approach. So we can use those copulas to model spatial asymmetry, and it of course also works in 3D, but it's just not very nice to visualize. And that brings me to my overall conclusions. So what did I hopefully show you? I showed you that spatial asymmetry, or like non-normality or non-Gaussianity, is pretty much all over the place. So it's very rare that you find something which is truly symmetrical in a spatial sense. And I showed you different data sets where we could analyze it, and we could see that they are asymmetric. I showed you that you can use empirical copulas, and it's pretty straightforward to do that, and the spatial asymmetry function to actually analyze and quantify this spatial asymmetry. We can use the theoretical copulas and fit them to the observations, and then we can use them to simulate fields that show spatial asymmetry. What I didn't talk about, but it's just because of time constraints, but it's a very important point, is the impact on dependent variables. And by that I mean, when you think about modeling hydraulic conductivities or permeabilities, for example, and you then model subsequently flow through those fields, then the flow behavior is very different whether you have a Gaussian or a non-Gaussian field. So when you remember those fields with the very strongly connected high flow, like they could be flow paths, right? So they could be permeabilities that are strongly connected. You have a very different behavior of contaminant transport, of flow behavior in general through those sorts of fields. So there's a whole lot that can be shown on the impact on those kind of dependent variables. And yeah, it's coming back to the title. So normal is just very often not the best choice, because it doesn't allow you to analyze asymmetry or to model asymmetry. And I'm not saying that copulas are like the holy grail and are going to solve all your problems, but if you can see that there is asymmetry in your data, then maybe we shouldn't ignore it, because it gives us definitely more information, and it's very useful if we can use this information. Just a side note, because I'm not sure if anyone here uses Schlumberger's Petrel, but we at the center, we had a big project where we implemented that copula approach into Petrel, which is the software that all the oil and gas people use. So if anyone uses it and is interested in a version, we can get you one. Here are references that I can get you if you want. And with that, I want to thank you for your attention. And I'm open to questions.
Thanks very much, Sebastian. That was really, really interesting. Quite a high level, but I think enough to prompt some questions from the audience, I hope. So we will invite questions online, so I'll hopefully get some questions from the floor, and then I'll check the online questions as well, see who we've got. So do you have any immediate questions in the room?
There are the questions online. So thanks very much. That was really good. And you know, I have to say that it's a little bit rare that I actually follow and really enjoy a talk on statistics. So it's a real compliment that you've made it really interesting. Though I hope there isn't a test. my question is, and I know you touched on this a little bit, but how are you applying this? And I'd be interested to know whether you've done any sort of quantitative estimates. I mean, in an actual, say, modeling, real world modeling situation, and whether you've made any assessments of the extent to which it's more effective than traditional methods.
Right. Well, we applied this to a lot. So back in Germany, because I'm from the environmental engineering side of things, and I did my PhD in the department for hydrology and geohydrology, we used it for those groundwater quality parameters. And there was a comparison study where they used Kriging and sequential Gaussian simulation and copulas. And when you do this and you do a cross-validation, for example, the copulas perform better. But cross-validations are always like, oh, well, yeah, you are a little bit better in terms of like estimating a point value. But that's usually not that important in my opinion. In my opinion, it's more important to get the overall spatial structure right. And that is something we did at the center, where we get data from the coal and gas companies and we analyze that, let's say, coal thicknesses, right? And they have very big problems of like estimating how coals are connected between the wells. Because if there is asymmetry in this data and they use whatever is available, like sequential Gaussian simulation, they just can't model this. So we analyzed this data and there is a lot of asymmetry in it. And I had a project with Aero Energy. They gave me some of their data and I simulated them hundreds of realizations of possible permeability fields, got them back to them, and they did some subsequent flow modeling, which I didn't see because it was confidential, but they told me that the results are much better than what they had before, whatever that means, because as I said, like they didn't share it with me because it goes into the production side of things, and that's where I'm out. But yes, so you can we apply this to a lot different stuff. Yeah.
In essence, it's of great economic significance to get the asymmetry before.
Yeah.
Particularly. So that's at the coal reservoir. And side of things, it's also highly fluid, channelized reservoirs where the behaviors are dominated by a connected and not by read problems.
Yeah, great. I vaguely followed it, but it's well outside my expertise. But I guess my question is probably similar to Rick's in a way. If I would love to see you take the DEM of the Ukraine, point sample it, and then use your approach to see if you can reproduce that structure.
Yeah.
Because another way of representing that structure is with fractal approaches.
Yep.
And I'd like to know how the two compare with one another.
Yeah, that makes sense. I mean, there are other approaches out there, like fractal approach, for example, or multiple point statistics. They are all able to simulate non-Gaussian spatial structures, but just like every approach, they all have drawbacks. Like so does the copula, right? So if you don't have enough data, it's very hard to get anything out of the data. But it's the same for all the approaches, right? If you have not enough information, well, you might see some asymmetry if you have a few data points, but it might not be enough to actually get a good fit of a theoretical copula to your data. Same with multiple point statistics. You have to have a training image. So the training image depends on how good your geologist is as an artist, really. So they draw you a picture and say like, well, that represents reality. And then you go on and start simulating. So it's nothing is really ideal, but it's just like a different way of looking at things. And I get your point with the sampling the Ukraine and just trying to simulate it. Could do that. Could try that.
It'd be a nice experiment.
Yeah.
I guess the one thing you get out of it would be what point. Where do you have enough data? At what point do we have enough data? That's a really big question for geologists.
Yeah.
Is what point do we not have to worry about collecting more?
Yeah.
But that's just ridiculous. That's sort of like a whole day. So for us, that's really just decision makers where. And then what we need to know is what is the where visualization is where the best chance of doing it. And if you don't have a decision, you can go back and still. Without a decision, it's an unanswered question.
Is it possible to go back to the Ukraine?
Sure.
I kind of feel like I want to be there now.
Yeah.
We've been talking about it. Well, no, like visually. So just to check that I understand the goal, or we all understand the goal, the claim is following on from Steve's question, that if we take partial amount of that surface, any of these really, yeah, there you go, great.
Yeah.
So if we randomly sample that, then give that data to you and give your data to someone less creative who's using multivariate normals, then the algorithms run by you will beat that other one to predicting what the rest of this shit is like.
Well, kind of. I would hope so.
Yeah, probably, based on performance so far.
It will create structures that show you the observed spatial asymmetry. That does not mean that I reproduce that exactly, right? Because it's still stochastic. So only if you sample very densely, we will get very close to that actual elevation model, right? But because you want to simulate possible realizations that are conditioned on your observations and conditioned on the observed asymmetry and variogram and all that stuff. So yes.
But the idea is that the Gaussian version has a fundamental flaw, which so that so that yours will converge quicker, we'll have a better chance of actually getting it right, essentially, which is all we're interested in the real world in the end.
The Gaussian one just cannot, by definition, it cannot have asymmetry because all the equations that are in the background are symmetric. Okay. So that's why everyone uses those log transformations. So because if you transform it into log space, they are log normally distributed. So they have log normal univariate marginals because they want the symmetry in those marginals because they need that. And then when they do the actual simulation part, so at each location where you want to have an estimate, you calculate a conditional Gaussian distribution based on your variogram and your mean. That's it. So, and that conditional Gaussian distribution is by definition symmetric, and then you sample from that and assign the value there. So they can get, as I said, like a little bit of asymmetry just randomly, but to get significant asymmetry, you have to be able to actually represent asymmetry in the functions that are underlying those techniques.
So my question is, in the case of the Ukraine drainage basin, you've kind of convinced everybody, I suspect, that the algorithm has got enough not asymmetry to get it pretty close if you had a lot of data for this area. Could it do the surface of Mars?
Good question. I have to try. I mean,
I'm only asking because at the end you said, oh, we can simulate any kind of asymmetry we like. So I immediately decided to ask that question. It's a bit mean, but I'm just really interested to know what you think.
Probably not quite, to be honest. Yes.
And also microphone. Yeah. Keep on mic. Oh,
sorry about that, guys. And remember what the direction where we're coming to this problem from is that we're really interested in the connectivity of the high, particularly the Polyperm values. The connectivity of the high values dominate our economics. Absolutely dominate them. So if you don't, and they're never symmetric, as Sebastian's proven many, many times. But we continue to use Gaussian because there's a pull-down menu with a click box on it, right? So because everybody does that. And so it becomes exceedingly important if the what would you call, we call it connectivity, but if that asymmetry is extremely important economically, so if you're just digging it up and looking at bulk properties, you probably don't care. But if you're chasing particular sweet spots or high perm streaks in our case, then it's critical that you get your best a priori estimate of where it's most likely to be before you sink a several $1 million well.
And coming back to the mass thing, I mean, I get your point. But that's why I said, like, it's not the holy grail, right? So there is more than just the first 3 moments even, right? So now we use mean, variance, and skewness. But that's not it. Like, there's the 4th moment, the 5th moment, the 6th moment. No idea what they actually are. I know what the 4th moment is in univariate, in a univariate sense, but no one has come up with a equation for a spatial 4th moment. And I think you need that. You need to go even further in order to be able to really describe those complex structures, because we are still very limited. It's just like a tiny step closer to be able to represent what is actually going on. But there's way more than just asymmetry.
Thanks, Sebastian. Gordon Forbes here. Very nice, clear talk. So I think my question probably follows on a little bit from the discussion which has been going on, and is a bit, probably will come back to what question are you actually answering. But I think what it was drawn to is in your responses, you say you've captured this structural sort of spatialness of the data set, but as I understand, you can essentially recreate many different models essentially of that. So, obviously then if I've created a model, but I can go create another one and they've still got the same geostatistics, how do you use that? Are you just sort of running lots of Monte Carlos and then sort of looking at a probabilistic approach and saying, well, based on all of our models, this spot is there? Or is it, I guess, again, it comes down to the question, are you looking at things high level or low level? But a bit more of what you guys actually do in that space would be great. Thanks.
Yeah, it's a good question. It comes back to what are you trying to do with that, right? So if you are just interested in where can I drill next, then you could use a Copula interpolation, for example, which would give you pretty much like a confidence interval of your values that you can expect at a given location. If you are interested in what is the flow behavior, and you want to do want to be able to have an uncertainty range in that regard, you need, let's say, 100 or whatever realizations, which you then use as input to your flow model, and then you get the uncertainty in the outcome of the flow model, right? So it depends really, what are you asking and what do you want to use it for? Yeah. So in our case, we want both. So we want to be able to say, well, it's more likely to hit coal here. And then we also want to say, like, well, we think the connectedness between the different wells is this and this, and that's your potential outcomes of water production, gas production, whatever. Yeah. So we need both things really. Yeah.
No, I was going to try and get to some of these people.
Yeah. So it comes down, so the second one, so the multiple flow modeling, it comes down to reserves classification. So you get a better uncertainty distribution, sorry, a more confident uncertainty distribution around your reserves. And the other one is you've got a better economic decision because you have a weighted confidence factor about both the cost and the recovery factor for a particular well. That's really what and numerically, or from a mathematical point of view, you have a better estimate of uncertainty. It's all about estimating uncertainty at the end of the day.
Sorry. Thanks very much. We have got a few questions online, and we've got embedded questions online, which is slightly sneaky. So I think we've got answered some of them, and some of them may require an additional presentation from you, I assume, to answer. So I don't know if there was something you wanted to pick your, I saw a simple one that was just about time, which is simply the computational time associated with Copula geostatistics compared to is that something that you
that's a good question, because It is higher. There's more maths in the background, way more maths. So it is slower than Kriging or sequential Gaussian simulation. But for that plugin, we had that issue that I write my code in Python, and it was incredibly slow. Especially when you come to those large models that they had with like 1 million cells, and you are like sitting there waiting for 2 hours to get one realization. And they were like, well, if you want to get this into Petrel, it has to be faster. So I rewrote a lot of that stuff into C++, and I applied a lot of mathematical tricks that my old boss told me, which helped a lot. So we brought it down to like 5 minutes from 2 hours. 5 minutes is still like 5 times as much as sequential Gaussian simulation, but it's feasible. Like, you can wait for 5 minutes without growing old. So.
Okay, yeah. Excellent. I think just in the interest of time, I think we might close off the session now. And maybe with some of these questions, we do get a transcript, so I might forward them over to you, maybe to answer directly. Yeah. That'd be great. So if you could just join me in thanking Sebastian one more time. Thank you again.
Thanks.
Just next week, which is our last seminar before Easter, Friday the 26th of March, we have Dr. Evelyn Mervyn from Anglo-American and 2 UQ PhD students, Thomas Jones and Jordan Petrias. They're going to be presenting their work on the role of microbial processes in carbon storage and in kimberlite rocks and tailings. So we're going to look forward to that and hope you can join us then as well. So thanks very much. See you next week. Thank you.